Department. This time I have the pleasure of introducing to you Joshua, who is a PhD student, PhD still, right? Mm-hmm. PhD student at CMS, under the supervision of our colleagues, CMS colleagues, Giovanni Franzoni and Andreas Pfeiffer, both here. So the idea of the project, you have understood it already from the announcement, which was kindly provided, the abstract that was kindly provided by Joshua. Is to present you VyPR. I guess I am spelling it right. VyPR, which is a very interesting framework to make a performance analysis of Python coding. I guess that this is the reason you are all here. Just a few comments. We are getting the presentation recorded. It was agreed by Joshua kindly. So we will have the possibility to, or you can share the understanding that this is being recorded with your colleagues, and the recording will be available in a few days after the talk. So I guess since on Thursday is holiday, it will be Monday, early next week. The slides, we got them already in PDF format, so if Joshua agrees as well, we can put them pinned on the Indico event. The usual stuff when we are recording, please, when we have a presentation actually, is please switch off or put your telephones on silent mode, at least we don't get disturbed. And when you have comments or questions, please use the microphone which is next to you. You have to push the red button to get it on, okay? So like this we get the question and the remarks recorded as well. About when to do that, I let it up to you. Whether you react online, you react to the questions online or you push them to the end, I let you choose it.
Yeah, I guess if you want to, if it's a quick question, then sure. But if it's getting longer, then we can maybe put it at the end.
So it's the usual style, yeah? I think that's all. Let's enjoy the talk. And let's go for it, yeah?
So thank you to everyone for coming. Thanks for taking the time to come and watch this talk. So as Miguel said, I'm a PhD student in CMS, and I've been working between CMS and the University of Manchester, which is my home institute, to develop this new framework that sort of takes some theoretical parts of computer science and then tries to put them in the engineering perspective. So I'm going to start by introducing this new approach that we have called analysis by specification. This is a new kind of formal mixed with applied approach to actually doing some performance analysis. I'll then discuss the tool that we have for applying analysis by specification, which is VyPR, the tool that is in the title of the talk. So this will then necessitate the rest of the talk, so we have to do some specification because, well, analysis by specification kind of implies that we have to specify something. And then I'll talk about some things that aren't as obvious, for example, instrumentation and monitoring. And then the last bit will be about a verdict server, which lets us do the analysis that we've talked about. And then a more recent development is an explanation mode for VyPR. So if your system doesn't satisfy the specification you've written, looking at ways to explain why it didn't. And this is relatively new work. So I'm going to start with analysis by specification. And the general idea is that we take some quite niche area of computer science called runtime verification, and we apply this to do some performance analysis. So this is in contrast to much more formal, concrete verification methods. So some of you might have heard of stuff like model checking and checking systems with respect to concrete specifications written in logics. And the idea of runtime verification is that it takes a slightly different approach. So instead of verifying the whole system and the model of it and doing complete concrete verification, we just let the system run and then check it with respect to the specification that we've written. So in our case, we care about individual functions in our system, and we check these with respect to a specification that we've written before running it. So importantly, as I've said, this is not formal verification. This isn't concrete verification. If something passes a specification with VyPR, that doesn't mean your system is correct. It just means that it performs in the way you want it to, unless, of course, you define correctness as being performing in the way that you want it to. So fine. Also, this components testing, so this kind of goes hand in hand with the fact that we aren't doing concrete verification. It's kind of a testing mechanism. So historically in CMS, performance analysis has been a manual effort. So you profile some functions, for example, in your Python service, then you get these into a database and you can plot time series and you can make some plots. And so in this diagram we vary some parameter And then we plot some data that we extracted. And we can answer questions like, when did the execution time of the function execute some time t? How often did it do that, and for which inputs? And this is great. But the key problem here is that this is often done with natural language specifications. So you have an idea in your head of what you want to check in your system. But somewhere like CERN, where you can have 10 different people in the room with 10 different mother tongues, therefore 10 different understandings of what the same sentence means, probably even if you do that with 10 British people, they will have a different understanding of what the sentence means. So this is generally a bad idea. Sorry for stealing your drug address. So the idea that we've taken is to specify these performance requirements in a formal specification language in a logic. So this removes ambiguity that's inherent in natural language. So in natural language, when you write something down, different people could have a different idea of what this could mean. With the formal specification language, this doesn't happen. There's a concrete semantics that says what it means. And further, this is the most important thing, we can algorithmically check it. So if we have a fixed syntax of how our performance requirements will look, we can have an algorithm that will consistently take any performance requirement that I write and check the system with respect to it. And then finally, this will come up at the end of the talk, but this means that we can do explanation more easily because we have more precise structure to point to when we think about explaining performance of our system. So analysis by specification is the kind of foundation concept that VyPR is based on. And then there's some extra stuff on top that allows you to do more sophisticated analysis. So you start by writing your specification, and then you check your system at runtime. And this tells you how well your system is satisfying your performance requirements. So VyPR primarily is research output, because I'm here to do my PhD, and so VyPR was developed as part of my PhD, so it's research. And it's so far characterized by these two publications. So the first one says quite nicely that, as far as we know, this is the first application of runtime verification in high-energy physics, which, given that runtime verification is quite niche, this probably wasn't hard to be the first time doing it, but still, it's a nice thing to be able to say. And also, we have a second publication that has some quite language-agnostic theoretical foundations. So I said this is taking stuff from theoretical computer science and applying it to the applied setting. And this is the publication over here that does that. So we set up the mathematical foundations, and then we build something using it. And the key thing about the VyPR project in general is that it's research in the environment that it's being used in. So runtime verification suffers from this problem of people in their offices writing papers and coming up with theory on how to do it. But applying it is kind of hard. And this is the same for formal methods in general. But VyPR is quite a nice, refreshing change because we're developing it in the context that we will need it. So this means that the use cases surrounding us at CERN, which is one of the reasons I'm giving this talk, can help us to develop VyPR and make it as useful to actual industry as possible. This is the bit that matters to you. So VyPR as a development tool, the idea is that we have all of this mathematical foundation, all this rigorous stuff that makes things work. But importantly, does this work? Hey, you don't need to know any of it. So it just works flawlessly, well, hopefully flawlessly. It works as well as it's supposed to, right at the bottom. And then you have all this machinery built on top that lets you do your analysis in your specification, and it just works for you. So you don't have to worry about the results, the mathematical formalism the system is using. And I think this is probably a good idea, right? So another contrasting thing is that when people give talks about runtime verification and tools that they've built, one of the things they always say is that, well, this system has to be used, when the system is being developed. And for us, this isn't the case, because we're not checking sort of these kind of correctness properties. We're just measuring performance. So you can do this at the end of your software development cycle, and that's fine. In fact, the application that I'll demonstrate later, we did. So this is a quick diagram. I say quick, it's not quick. A quick diagram of how VyPR looks. So this is for the web service settings. So the stuff I'm presenting in this talk will be web services. I probably should have said that earlier. But so on the left, we have the service level monitoring. And on the right, this is difficult. And on the right, we have a central verdict server. So importantly, the stuff in green is the only thing that you have to care about as a developer. So everything else is completely automatic. I'm probably walking. Am I walking in front of it, or can you still see it? That's good. Right. So the stuff in green is the stuff that you have to care about. So you write your specification. The system is then instrumented, so you can take data from it. So the VyPR can take data from it. The monitoring is done automatically based on your specification. Then all this data is sent to a central repository for later analysis, and then you come back into the process when you do your analysis. So all this stuff that isn't in green is completely automatic and done by VyPR based on the mathematical foundations, and we've already shown that this works just fine. And the box at the bottom there, I should probably just start pointing at this. The box at the bottom there with the dashed bordered rectangle, this is stuff that we're working on at the moment. So one thing you'll see later is that work that we've done so far shows that we need to do a bit of work on our analysis tools for it to be really powerful and useful to people. So I'm going to start by giving a bit more detail to the service level monitoring. So we have a specification, which is what you would write. So how does this look? Because I've been talking so far about how specification would work. I haven't shown you anything about it. As far as you know, you just wave a wand and it works. Well, I'll show you how that works. We have monitoring, which I won't talk about in a great amount of detail because it would take up a whole other computing seminar, and I don't think anyone has the sanity for that. So I'm just going to discuss it briefly. And then instrumentation, because that's really important. So specification has historically been a tricky thing, because when people design these systems, they take specification language that already exists. So if anyone knows anything about model checking, we have things like linear temporal logic, metric temporal logic, all these existing specification languages that were developed in extreme abstraction. And so when you take these and give them to an engineer and say, oh, describe your system using this, probably they won't find it easier, they'll just get annoyed and then they'll give up. So to fix this slightly, we invented a new logic called control flow temporal logic. And the idea behind this is it's a mathematical logic, so it has the same rigorous theoretical foundation as all the other logics. There are proofs that it works in a certain way, but it's really useful for engineers. So it allows you to think directly about how your system works. And this is the contrast to the theme that runtime verification has been following for the past few years. And of course, VyPR provides you with a library to express these specifications that you have in Python code. So you give these to VyPR, and then VyPR does the check for you. This is what it looks like. I'm going to go through this slowly and in steps. I'm not just going to show you this and say, please understand it. So this is the general idea. You can see at the top we have some strings. And the idea is that we have this tree structure of our service. So if we have a web service made up of different functions and methods, the idea is that you write a specification over each method in your service, over each function. So at the top you have a module, and then you have a function, and then you have a list of specifications that you apply to that function. And when you write this in VyPR, the data that you get on your separate verdict server will reflect what you wrote, and you can see how well these specifications are being satisfied. So this is the first example of how PyCFTL works. So at the top, I have a natural language version of my specification. For example, I might want to say every time val is assigned, the next call to the function is show data. So this thing here should take no more than 3 seconds. So I do this by first, I imagine the runtime of my function as a sequence of events, as there's some kind of timeline. And then I have this selection of points of interest. So the idea behind CFTL and PyCFTL is that you first select your points of interest, so this bit, and then you give a function to evaluate at each of those points of interest. And VyPR will apply this function once it's derived the points of interest at runtime and check whether this is satisfied. So this is the general idea behind PyCFTL. It's a straightforward thing. You pick points that you care about by giving a criteria that they should satisfy, and then you define a function, like this one, that decides whether or not they satisfy the rule that you care about. So let's go in a bit more depth. The check function that we have. So the idea is that you derive some points of interest, and then you give a variable. So if I go back, I have this q here. So that means that if I give a variable q here to this lambda expression, then that will be given every point of interest that I found at runtime. So in this case, I asked for changes to the variable val. So in this case, I can think in this bit of code here, q is a state that is a change to the variable val. And on this state, I can ask for the next function call. I can look forward in time. I can navigate through the time that's present in the runtime of my system. And in this case, I can see, well, for every change to the variable val, I want it to be that the next call to this function called show data took no more than 3 seconds. And this is a general idea of writing specifications in this language. To make things a bit more complex, so in the previous example, I just have the next call to show data. In this one, I have unbounded future time. So I start with each change to val, and then I reach forward as many times as I can do to every future possible call. And this will be more useful in a second when I show you the next specification alone. So in this case, the code that I've given here is slightly different. We have two variables. So Q, as before, is a change of the state. So every time this variable val is changed, I bind it to this variable Q, and I have Q here. And then T, this time, is given for each future call of show data, is given each of these. So I end up with a list of pairs. And then I can evaluate this function at each of those pairs. In this case, I don't care about Q in this specification. I just want T to take no more than 3 seconds. Now, this is where VyPR begins to be a lot more powerful than standard profiling techniques. So often what you would do when you want to profile a service is you decorate functions, you put all the data into a central database, and then you make some plots. However, what if you want to make sure that only the functions on a certain branch in your code followed a certain constraint? So it might be that there was a certain branch that corresponded to a certain database connection, and you only place that constraint on that branch. All the other branches might be far quicker, and so you don't need to check their performance, or they might be a lot slower, and so you need a different constraint. And so here, I can do an if. I can say, OK, if this branch is followed, if this variable is equal to true, then I apply this specification. And this takes a lot of the work out of if you just wanted to get some data out by profiling functions. Because in this case, I can actually write it into my specification and say, well, I only want this constraint to hold if this branch was taken. And this is where YCFTL begins to be a lot more powerful than normal methods. So now a complete specification hopefully makes a little bit of sense based on the ridiculously quick explanation I just gave you. So you have at the top, this string-based hierarchy that VyPR uses to find which function in your service to apply to. And then you have the specification, which selects which asserts that something should be true during the runtime of this function. So importantly, apart from adding a line to your service saying that VyPR should be activated, the important thing is that all the functions you want to check and all the parts of your system you want to verify, you don't have to modify them at all to check them with respect to this specification. So you write the specification, and then the source code is completely left alone. The instrumentation is done completely automatically by VyPR. You don't have to worry about that. You just write the specification, and then everything is done by VyPR, and you get the analysis out of the other end automatically. And further, all of this is written in one single file. Obviously, if anyone at some point says, well, we'd prefer it to be split across several files, then we can do that. But at the moment, we do it like this, and it's proven fine so far. So I've been talking about this idea of extracting state and time from the run of a system, but I haven't actually said how we get that information. So we need to address that. So given this specification, how do I get these states? How do I get these calls? What do I do about it? And moreover, how do I make sure that I observe just enough, but not way too much? So the first option is trace functions. So for any of, I was going to say for any of you who work with Python, probably that's all of you, given that you've all come to this talk. So normally we have the Python interpreter, we can give it a trace function, and then for every event that happens at runtime, this function is called, and we can execute some logic. This is a really nice idea, except it's got potentially huge overhead. Because if we're doing any meaningful logic inside that function, we're doing this for every single event that gets executed at runtime. So if we don't want to obliterate the performance of our service before we've even measured it, this is a terrible idea. So this gives the very strong need for instrumentation. And the whole point of this is that we insert new code into the existing code, and this will give us the information at runtime that we need to check whether the specification is true. And VyPR does this by first performing static analysis based on the specification. And then, so you get the static analysis, you work out where in the code you need to insert instruments. And then you derive the abstract syntax trees. You have this repository of instrumentation code. For example, the specification that I had before measured duration. So this is one kind of code. This will be code that measures time. If the specification cares about state, then it will be a different kind of instrumentation code because, well, this will just record a variable value, so the code will change. So I take this relevant code, I compile that into an abstract syntax tree, and then I put it into the parts of the program that static analysis has told me that I have to. And once I've done this, I compile it to new bytecode. And this new bytecode is instrumented so that we can check the specification that we care about. So now we need to address monitoring. How do we actually decide if a specification holds or not? And this has to be done well, because if you do this too slowly, you're doing it at runtime, and so potentially you would destroy the performance that you're trying to measure. So the only thing I'm going to say is that CFTL's monitoring algorithm is efficient, because we make use of the fact that we know where things are statically, and this helps us to be a lot more efficient. I'm not going to go into it in detail, because as I said before, no one has the sanity for that or the time, so I'm just going to skip it. So in terms of implementation, the idea is that VyPR sets up a separate thread along from your main service, and then we have an intermediate consumption queue that the instruments send data to, and the consumption thread runs the monitoring algorithm and decides whether things are working. And as I've already said, CFTL specifications are written over individual functions. And this means they're written over individual threads. So we don't do specifications over multiple threads because there's been no need for it yet. And also this means that the information sent to a central verdict server for analysis is done at the end of a function call. So we almost have a complete architecture for performing analysis by specification. We now just need to detail how this verdict server is going to work. This I'm going to leave out because, well, it doesn't exist yet. And this I'm now going to talk about. So we have this verdict registration API, which is just an API. You all know what that looks like, so I'm not going to talk about that. And then we have a relational verdict database, which really allows us to put everything into an efficient structure and do the querying on it that we need to do analysis. And then I'll show some screenshots of the web-based application, but it's just a web application. So the verdict database is structured based on specifications and based on how they relate to the runtime of the system. So the top level is a transaction. So normally this is an HTTP request because your web service probably deals with HTTP. The second level is that we group everything by functions and then the properties. So because you can write like multiple functions over the same, multiple properties over the same function, I group by this. And then you can group by calls to that function because there might be multiple calls to the same function during the same HTTP request because your service is split up into multiple functions, and this is a pretty common thing to happen. We then group by points of interest, and this is a useful thing because it might be that one change to this variable failed your specification, but another one further along the line didn't. So you need to be able to split this information up so that you can look at the appropriate level of granularity to be able to decide where exactly in your code things failed. And the next thing is really important because we need to know at which point in our specification, at which point of observation, things failed. In this case, this is particularly useful because say this is not satisfied and we go down, say this is to check branching, and we go down the branch where val wasn't equal to true, then everything is true and everything is satisfied because technically no function call ever failed our constraint. And so we would get true in the verdict database, but then we would also get true if this was true, and then this function call also satisfied our constraints. So this is two ways in which our specification can be satisfied, and we need to be able to distinguish between this. So we do. In the verdict database, we store at which point our specification was satisfied, at which observation made it be satisfied. And now I'm just going to show you some screenshots and point to how you can actually use all this analysis stuff, because from a software engineering point of view, that's what matters, right? So this is a nice web page which just looks really obviously like it was made in Bootstrap, because that's pretty much the only web building thing that I knew about then. So yeah. This is, if you want to search by first exploring your specification and then working out which verdicts it generated at runtime, you can do this. So on the left, you have your specification, which is grouped by the functions over which you've written it. So in this case, I had a really simple specification. I had one property written over one function, and I can select it here. I then got all the HTTP requests during which that specification was checked, and I can select these. As you can see, timestamps is not very useful, and this is part of the whole we need to make these analysis tools better motivation because, well, timestamps aren't very good for humans. So, and also then function calls. So as I said, there might be multiple function calls inside the same HTTP request. Then once you've done that, you get a list of verdicts. So as you can see here, you have line numbers as well, so you can really see which parts of your code did what, basically, and which parts of your code satisfied the specification and in what way. And now you can go back the other way. So you can fix a verdict and then find out which bits of your system resulted in that verdict at runtime. So I think this is probably slightly more useful than the other one, because quite often you're just going to run your system with this specification attached to it, and then you're going to want to know when did things fail. So this is doing that, right? So you select violating, and then you select a part of your system that you might care about. And then on the right, you have the list of parts of the specification that generated this verdict. Now we have the architecture. The architecture is finished, at least for this part. So now, I'll tell you how this has helped so far. Because I'm not just going to come to you with a system and say, I promise it will be useful at some point. Instead, I give you evidence as to why it's useful. So first of all, VyPR has profited a lot from being developed at CERN. As I've already said, this field suffers from being developed more on the theory side. And then when you want to actually implement it and apply it, that becomes difficult because it's often not done in industry. This is a really good thing about this project because we did it in industry. So the first major application was to critical infrastructure at CMS. We took the service that we use for uploading non-event data during LHC runs, which is conveniently for us a Python web service. And then we monitored it with respect to a specification. At this point, I should thank Giacomo Govi from the alignment and calibrations group, because he basically helped us set up the database infrastructure that let us do these tests. And all these tests are detailed in a paper that was in TACAS 2019. And in this paper, we took 6 months of LHC runs of conditions upload data, and then ran VyPR over the upload service and saw what came out. Also, really importantly, this was done while inducing not a lot of overhead. So the overhead was really small, which means that in a real-world system, this thing works. So a bit of context before I show you the results of that application. So at CMS, we have non-event data uploads, for those of you who aren't familiar with that. The idea is that during LHC runs, we take the alignment and calibrations data, we put that into a central database, and that's made ready for physics reconstruction. And then VyPR was used to do analysis on this service, and well, it turns out that we found some pretty important performance drops. So on the left, the y-axis is the number of violations, and the x-axis is we take the same data set of uploads and then rerun it with different delays between the uploads. So you can see that there's a bar on the left where somehow, when we left less time between uploads, things took a lot longer. And so this is something we're going to investigate. However, this isn't as important as the one on the right. So you can see there's a pretty obviously big bump here that's an order of magnitude bigger than the other ones. So on the x-axis, we have functions versus property pairs. So I said before, we compare these two. So I select a function, I fix a property, and then I put this in a pair, and this is how I get my y-axis. Sorry, my x-axis. And then on y, again, we have numbers of violations. So in this case, you see that this bit of code here, which was supposed to be an optimization, was actually failing miserably for some of the uploads. So this is quite a large percentage, and we need to fix this. So this is an example where VyPR is already, by doing relatively little work, VyPR has shown us quite a major performance drop. And the lessons learned from this are that, first of all, our analysis tools need to be better, because these plots were quite clearly not generated by the web application I just showed you. This was done by writing scripts, and that wasn't fun. So I'm not going to make developers do that every time they want to do analysis with VyPR. So we need to do better at that. Also, we need an explanation mechanism, because I said at the beginning that we really care about VyPR, first of all, saying to you, okay, well, your system failed to satisfy these specifications at these points in time, but I'm not going to tell you why. I think everyone would be quite annoyed by that. It's like when C++ gives you segmentation faults and doesn't tell you where they are. It's incredibly annoying. So now we introduce an explanation mode for VyPR. So the idea is that we want to identify regions of code where the code I've run that traverses these regions of code might be more likely to result in failure of specification. And I'm going to give a simple example. So consider this specification on the right. I look at all the calls to show data and require that they take no more than 3 seconds. And here I have a call to show data. And then I have two possible branches. So I have one branch here, and then two branches there. And I'm guessing everyone in the room already saw that. I would be surprised if no one did. But yeah, so we have this specification, and then we think, well, it might be that if we run this 1,000 times, that using this branch always causes failure, whereas using this branch, it doesn't. Surprise, this branch makes things fail. I didn't set that up at all. But yeah, so we can then use distinction between paths to decide on whether or not certain regions of code fail specifications. VyPR implements this really efficiently. So in space, we don't duplicate path information. Of course, we have to store all of this path information somewhere so that we can do analysis. We don't duplicate any of it. And in terms of time, we do path reconstruction pretty much as well as we can do at the moment. There probably will be some optimizations discovered along the way, but that's the whole point of a research project. And a key observation is that path reconstruction should become more efficient as you observe more data. Because the whole idea of paths through a system is that as you observe more runs, you can filter out the set of paths you have, and ultimately the search space becomes smaller because you're getting rid of paths that you know don't violate the specification. And so the whole process becomes more efficient over time. So in terms of integrating this into our existing architecture, we start with what we have. Then we add some more instrumentation. So this is path profiling. It's really not a new thing. We just insert instruments at branching points. For example, branches and conditionals inside loops, so we can precisely reconstruct the path taken. And then we modify our verdict database, because in the end, we need to be able to take observations and say, okay, well, for this observation, I know the system took this path to reach it. And then if I take this observation over multiple runs of the system, I want to know what were the different paths that reached that observation. And this is what this addition to the architecture does. So I start with path reconstruction across multiple function runs. I then do automatic comparison of common features. So I look at conditionals, loops, for example. Then at the end, I identify problematic control flow, and I relate this back to my performance specification. And when I say common features, well, what exactly do I mean? If I have two runs of the function, these two here, VyPR can automatically tell me that this was the point where divergence happened and where the specification might be being affected. So for example, if my specification is always failed, or most of the time failed, by this branch, then VyPR can identify the fact that this is a branching point, that paths diverge here, but they all go through this bit here, and then you tell me, well, most of your paths ended at this observation, but only some of them, the ones that failed your specification, took this branch, or completed this many iterations of your loop. So VyPR can do this automatically, and we can detect bits of the code that cause this. So all of this is some nice theory, but what we need to do now is put it into an analysis library, and this is what will happen in the next few months. So explanation has to be a really fluid process for the developer. At the moment, it wouldn't be because it's new work. So whatever analysis library is developed has to be made so that developers can perform explanation of their software's performance easily. And also, we're probably going to do it as a Python shell or command line interface project, because it's kind of evident so far that if you try and do this thing as a GUI, as a web-based application, you tend to lose quite a lot of flexibility. So it would make more sense to put it into a shell, or into a shell library, sorry. So to conclude, VyPR is a research tool. It's benefited enormously from being developed in an industrial environment, and it's already proven its utility. There are still more design decisions to be made, because I've already said that we need to build this analysis library. But leading into this, the theory is in a really good place. We have solid theory. We have theory accepted by the community, and all of it has been demonstrated so far to work. And so I come to pretty much the reason why I'm giving this talk. So we want to maintain this process of using the use cases around us to develop VyPR and make sure that it's developed in line with industrial needs. So we don't want to have this nice start and suddenly say, well, for the first few months, for the first year of VyPR's lifetime, we took into account what industry needed, and then we just got bored and decided to publish some more papers, and so we developed some theory on our own, and we don't know if it's any use to anyone. So instead, this is why I come here, to say to you, if you have any use cases, or if you think you have any ideas for what we could do with VyPR, or if you have any systems that we could use it for, then we invite you to work with us so that we can carry on developing VyPR as an industrially developed tool based on use cases. So that's it for me. thank you very much for listening.
You have fans in the audience. So, thanks a lot. Comments and questions, welcome, of course. The feedback. Proposals to join, to provide a use case. Well, I have one tip, which actually I have been tipped before the talk, which is that this formal mechanism to approach to performance analysis could be taken beyond runtime code. I mean, beyond Python, for instance, and could be taken to other languages. I mean, I was hinted that. So, would you like to elaborate?
Yeah. So, the theoretical foundation that allows all of this to work doesn't depend on Python. Obviously, there are some things that Python does, like giving us the abstract syntax tree for free in instrumentation that make our life easier at the moment. But the mathematical foundations are pretty much language agnostic. So, if there's another language that it would need to be applied to, as long as it's not a completely different programming paradigm or something crazy, we could still apply a version of VyPR. Obviously, we would change the acronym because VyPR is kind of implying Python, but yeah.
And is this the context for your second paper when you were mentioning the two? Is this just to give the formal mechanisms expressed in
so the
theoretical mode?
Yeah, so the first paper was the theoretical foundations.
Oh, sorry, the opposite.
And then, the second one was actually applying it. And then the third paper, a new paper, will be about the explanation mechanism.
Okay. So it's really, I find it very interesting, and I am a layman. So everybody's shy? Even the friends?
Thanks for coming.
So we have a question here.
Sure.
So you have limits like this function should not take longer than, say, 3 seconds. How do you deal with running these tests on different machines where the execution time is longer? So my machine might be super slow. Could I still run this VyPR tool? And
I guess it wouldn't be normalized. So yeah, if you ran it on a really super slow machine, you would have to change your specification. This is one of the reasons why we want to work with different environments, because so far everything's been run on the same machines. On OpenStack virtual machines, and everything has conveniently worked. This is one of the reasons why, for this to be a production-ready tool, we have to run it on different environments, because, like you say, the specification wouldn't magically realize that your machine is slower. So, yeah.
So, okay, let's take it.
So you have the one example of the duration of the function. Can you also check for return values or not raising exceptions and all these?
Exceptions, no, at the moment we don't deal with that, but in terms of state, anything that's state or time we can measure. So the specifications I showed were quite simple. And in fact, the full definition of the logic, the formal definition, allows you to be quite expressive. So you can say, okay, for the next function call, I care about the state that's generated as a result of that function call. And you can link all of these things together with propositional connectives and write some quite complex formulas. So to answer your question, yeah, you can.
Very good. I think we are ready. Okay. So before thanking again Joshua, I just remind you, I have an event to announce over the next couple of days, because it is not the agenda is not completely finished yet, which is the CERN-VM Users Workshop next week. It's from Monday to Wednesday. In particular, there will be talks during Tuesday that might interest you. You can already go to the seminar's website to see the 3 that I have been told so far, but there will be another 3 talks. It's just to let you know, since you are here, to let you know that it is already, that you could already foresee on Tuesday to participate at some of these talks. It will not be here. It will be where they have arranged the whole event, okay? So with that, thank you very much for coming. Let's thank again Joshua for his work. And see you next time.